I hope you can hear me. Yes. Wanted to thank you for your time here. It's Saturday. Greatly appreciate the fact that you're spending your Saturday at CASPA. We've been a partner with CASPA, and they do an outstanding job of getting companies and folks together in order to communicate and take things to the next level. So today I'll talk about enabling semiconductor design and manufacturing. We are classified as an EDA company, but I would rather be classified as a digital twin modeling company going forward, and I'll tell you why shortly. Because we use AI, and that's all we do. We create models that can be simulated accurately, and products can be done based on those models. Just thought it's a good idea to talk about some points in the history of AI, and of course, this picture, the resolution of how things have happened is very coarse. But there are three parts of this that I wanted to actually bring up. One of them being in 1950s, Alan Turing devised a test in terms of artificial intelligence. And when I asked the new college grads or new PhD students, do you know who Alan Turing was? Some of them do, some of them don't. Then I asked them, do you know anything about Alan Turing test? They say no. Then I asked them, have you heard of the imitation games, right? Anybody here has heard of the imitation games, right? And then they say, oh yeah. I said, that's what the Alan Turing test is called, the imitation games. It used to be called. And then they say, oh yeah, we know it because it's Benedict Cumberbatch. So they know Benedict Cumberbatch, and they associate Alan Turing to Benedict Cumberbatch, who was the actor in the imitation game movie. But the point of it being is, it's very critical to understand where this stuff come from. And the reason I bring Alan Turing is because he was a genius of his time, but more importantly, the simple imitation game that the test came about. None of the AI systems on the planet that exist right now could even pass it. In other words, the test it's a very simple test. Even if you think of ChatGPT 3.4, maybe they have passed it 1 or 2 times, but not consistently. So in other words, we are at the very early stages of this. We have actually quite a bit of shortage of quite a few things that needs to be developed and get us to the next stage. But that's where it started, in my opinion. And then you find, I used to love to play chess, and I was champions of my, region, district at a very young age. And then all of a sudden, I hear in the news that, an AI machine called Deep Blue by IBM defeats Kasparov. So that killed my enthusiasm about getting a job in chess, and that was a good decision, as a matter of fact. There's no money to be made in chess. And then later on, we hear that, IBM Watson beats up Jeopardy contestants, one of the champions, and we call that AI and intelligence. And then Alexa comes through Amazon, and guess what? After I hear that a kid could order 1,000 diapers to come to home through Alexa, I thought, oh, they're not context aware, so it's not working yet. So bottom line, there's a lot of glitch, there's a lot of work, there's a lot of effort that's getting put together in order to get us where we are. The shortcomings historically has been focused on application areas that really make money. There's no historical killer application that made money. We are in that era now. The good news is, there were limited computing in power. In terms of computing power, in terms of memory, you just heard stories that computing is not adequate. NVIDIA's of the world, although world class, $1 trillion companies, Semiconductor no one has heard of in the past, still lacking a lot of compute power as well as memory, right? Memory companies, we know that any compute, whether it's in memory compute or compute and memory, external or internal memory, it requires quite a bit of significant work. There's still work to be done. And then also, we did not have advanced algorithms. Right now, we're starting to have those. We did not have big data. What was the big data before internet, right? It didn't exist. So with that in mind, I wanted to bring up the fact that where we are at now. Where we are at now, we are addressing and enabling some of those shortcomings. Many great companies are working on compute power. And ironically, it's compute power. It consumes also a lot of power, but still not there. Many companies are working on, in memory, but also external memory applications that require high bandwidth, high capacity, low power. We are working on advanced algorithms, which we did not before. Amazon's, Microsoft's, Apple, IBM's of the world are working on that. And then also generating data. There's no shortage of data. Big data is there. IoT devices are everywhere. Even my, dryer washer can send message to the manufacturer to get maintenance done. And then also in terms of where the new generation of data is coming from, financials, from companies like insurances, medias, colleges, law firms, and so there's no shortage of data. And you've seen data, they've seen previous presenters that say that the growth of data is 100x per year, right? It's the fastest growing part of this whole thing. However, compute and memory are not at that rate, so that's where we need to get at. And the clear applications are many. AI anywhere, language translators, autonomous car, Waymo. Waymo is running at San Francisco, Austin, LA. It's scary to see some of these cars driving by themselves, but they do an amazing job. And last but not least, the reason I'm here is tell you a killer application that I think it's being picked up by many of the EDA companies is EDA, electronic design automation. So how do we do these applications, and what do we do with AI in terms of enabling the customers, reducing our own time to market, and being able to address the next generation of the problems and challenges. Here are the problems and challenges at the very high level. I consider them to be three components of them. One is, I call that increasing complexity. So geometries get lower, number of transistors increase, number of functions increase. And as a matter of fact, that's one of the biggest problems we've had to deal with Moore's Law, its limitation, and where we're taking the new packaging, new power integration, and so forth. The second part of the challenge that we deal with, every time we are trying to solve a problem, we have to, at times, introduce new material. You've heard of silicon carbide, GaN, and things like quantum dots, right? Quantum dots, if you have gone to Costco and bought a quantum LED QLED, that's quantum dots put on LEDs that form 1/3 of a component of a pixel on a display. If you put three of them together, that's 1 pixel. Then you have to do the panel itself. And however, what I'm trying to get at is adding new material imposes new challenges in terms of simulations, system requirement, manufacturing, and so forth. Huge challenges. And the third and the last but not least is go-to-market challenges. Getting to low geometry nodes, mask costs are high, wafer costs are high. Getting the design done takes quite a bit of time. And also, that applies to all applications on all markets. So I know EDA companies, including us, are addressing these, but each of us address them differently and solve the problems differently for different market applications. So there was at DAC a keynote talk by Wally Rines, who is the CEO of Konami, and he's also our independent board member at Silvaco. And he gave 3 levels of those AI application in electronic design automation, right? Again, electronic design automation. Focus being design, electronics, right? And I think the nomenclature of electronic design companies being still EDAs is wrong, but that's a philosophical question. We can talk about that for months. But the first thing that he mentioned is self-optimization tools. What can the tools do to perform better and help designers design better with the existing software that there are? And there are many of them, right? You can do training of specific capabilities, do efficiency improvements, and they're being done. They're being done by Cadences, Synopsys, us, and everybody else who has enough customer base to do that. The next level is not optimizing tools, but design assist. Can you assist the designer rather than when you're trying to design a phase lock loop and trying to pick up a phase detector? Can you pick up digital phase detector that has this kind of characteristics, phase noise, and blah, 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 blah. Can you do this sort of thing to help the designer? And the answer is yes. There are many, many, many tools that companies are working on to assist in designing of these functions. They're rudimentary. They're not still going to pass Turing test, but they're there. We're implementing them. The next part is, instead of assist, is can they generate design? Generating design is wholly the relic of EDA tools, right? Can you push a button and the design pops up, goes to manufacturing, gets done, and you have it? Voila. Are we there? Anyone? Are we there? No, they're not there. Quite far from it. But we are doing with what we have and what we can in order to apply deep learning, self-supervised learning to do what's called generative design. What Silvaco has done in the past 4 years, and we've actually announced this as of May, electronic design automation design, we are actually taking not only the challenges of design, we are taking our software and applying it to the manufacturing world, fab. So we call that fab assist. If you think of design assist, an equivalent part of it, if you help the fabs, is fab assist. We actually build digital twin of fab process and technology at wafer level. So if you think of companies like Dassault, a French company, they do digital twins of airplane. They do digital twins of a 3-engine airplane, which is my favorite airplane called Falcon. And if you look at how they implement this thing, you actually have a digital representation of this huge airplane, including engines and all of that, in a computer that they can simulate, fine-tune, and find problems with. Incredible. That's the sort of problem they solve. We talk about companies like Ansys. Oh, they do digital twin of car engines. That's the sort of problem they solve. And that's a dimension of the physical problems they can model. What Silvaco does, we do digital twins of anything from at atom level, atomistic, all the way up to, I would say in this case, a wafer for manufacturing. Or since we are actually a leader in display technology, anything from a single pixel all the way up to display panel itself. So that's the domain and physical size that Silvaco works on. So let me explain that a little bit more. And I think to do that, I have to tell you where we are, where we came, and where we are going in this with respect to the AI and digital twin modeling of it. So we do provide TCAD, semiconductor, IPDA, and if you look at the companies that fundamentally understand the technology aspect of semiconductors, it's an art form. Many people have forgot it. There's only 2 companies on the planet that understand fundamental physics, chemistry of technology of semiconductors, that they do technology computer-aided design. It's not an EDA, it's technology computer-aided design. And we are number 2 in the world in that respect. And we're number 2 in that respect because we focus on power, silicon carbide GaN, memory, and we focus on displays. Those are our 3 main things. We are in 7 different markets that are listed at the bottom, but those are our top 3 growing markets. So, and our position in the market is on our TCAD adoption. I think this is an automatic flip. And our EDA adoption for display, power, and semis is pretty good in terms of the size of the company we are. So if you look at what I see to get to the final chip, the first step to get to the final chip is what designed it. That's where for the past 30-something years, Synopsys, Silvaco has been around for 40 years. We've been working on helping customers to design. Where we are taking it to the next level is fabrication. As I mentioned, we have a new technology that's patented called fab technology optimization, fab technology co-optimization. Everyone in this room has heard historically what a DTCO is, design technology co-optimization is, but they've not ever heard of fab technology co-optimization. And you find out fab technology co-optimization sits 1 level below design because it deals with fab fundamental technology, fundamental process steps, and that's what needed to understand and have before a designer can use a PDK and models that could be 3 sigma accurate and do their design. So that has been missing, and that's where we're adding. And this actually will get tied not only to the fab wafer level, but also that digital twin of wafer is true in its nature from atomistic level of a process step. I'll give you examples of it all the way to the wafer, so you can give that digital twin that represents what the fab can make back to the designer, and the designer, as long as they're within that space of the model, they can design anything they want, and it's manufacturable at a high degree of yield and performance, so you don't have to go keep optimizing it, right? Cost savings is tremendous. And of course, the natural revolution or evolution of this whole thing is to do digital twin of packaging, testing, and the final chip. Then you really have control over your process steps and getting the next generation of things done. Examples of digital twin that we provide: memory arrays, going from matching the actual, I call digital twin, it has to be form, fit, and function. Form means it has to look like the same thing. Fit, it has to fit within the boundaries of where the physical thing fits, and it has to function the same way. So digital twins, the way we do it is physics-based, chemistry-based, optics-based. So meaning that all the properties associated with the physical world of something is already captured in your computer. So digital twin of memories, digital twin of displays for micro LEDs, digital twin of wafer, digital twin of foldable displays. These we do have, and we provide that to the customers. Very powerful to get them to the market fast. A lot of products that you see here, with the exception of the bottom right, digital twin of wafer, we've been providing that to our customers for many years. Their products is already in the market. We actually tend to work in the advanced technology nodes and R&D for our customers, and 95% of our revenue comes from their advanced technology, meaning that what you see here, we have been working on for the past 5 years. What you are going to see in the next 5 years is what we're working on now. So given that, here's what we do actually with fab technology optimization. Matter of fact, we announced a relationship with Micron. They're using this in their Boise fab. This is how we generate a fab technology optimization model, digital twin model for a wafer within their foundry. By, again, this is FTCO, not DTCO. It sits one level below DTCO. It uses design of experiments. It uses data from the fab. It uses AI to minimize the space and number of optimizations you need to do in order to get digital twin going. And it does a feedback until you get a good model for digital twin that can be used not only by the folks on the manufacturing floor to fine-tune their CPK and Z boundaries of yield, but also fed back to their designers so that they can design and explore existing improvements and next generation of products improvements. So no one has seen this before. So it's unique, it's new, and we have announced it. Here's an example of it. If you look at this, people who are familiar with the process steps of devices, you'll see this is called shallow trench isolation, and there's a terminology called self-aligned quadruple patterning, which is basically by every time you do photolithography and repeat that step with different patterns, you can actually increase the resolution without having the accuracy of the lithography to be what you want the final results to be. For example, if you need a 10 nanometer accuracy, if you do quadruple patterning to get 10 nanometer, that means you have lithography that can handle 40 nanometers. This is one way to do it. To simulate that, we are showing in shallow trench isolation, which is very, very important in a lot of these processes. The ratio of these, the spacing, we can actually do this through, we can see these knobs getting turned on to see how you can optimize. And this does it real time without having you to run a wafer. In other words, if you run those parameters on a wafer with these parameters we give you, and you stop and take a cross section, scanning electron microscope, it matches this. This is the beauty of this, right? And this is only one very simple steps of it. We talked about memory technologies. We talked about memory technologies having thousands of layers of process. This is one of the 1,000. We can do all the 1,000 layers. We can real time explore how this thing can behave, how it can yield. So it's very powerful. It's the dream come true to me. This is crystal ball. If I had a crystal ball of what my manufacturing can do, This is it. You can't find anything better so far. This is the best in the world you can have. Okay. Give you some feel for this, right? So where the data comes from, right? The data comes from design of experiments, process simulations, followed by modeling in ML AI. That enables you to do a real-time, that's the key, real-time DT modeling, right? That's the flow of the work. So in terms of, yeah, I don't want to go to summary yet. In terms of where these sit, you find out that we, as a provider of this FTCO flow and FTCO framework, we don't even see the data that our customers have because we don't want to see their data. We have models. They have the mega data that they have collected over the years for their fab. It's already there. We don't have to have them create new data. They train our models with their data. We don't look at their data again. That be secure, and we don't have to have access to it. However, what turns out to be the model we generate is the work that has gone through training, running some wafers, and understanding how this process works in order to do real-time control, real-time understanding of how you can, if the fab is running and one of the equipment pieces has gone and needs gone out and needs maintenance, we actually can predict that. Tell them that this piece of the process is falling outside of your CPK and Z. Go take a look at it, right? Rather than flagging something before, right after it fails, we tell them this has a potential of failing, so go take a look at it. So to us, we are very proud of this. To us, that's why we want the company to be known for a digital twin modeling company, not an EDA company. This is beyond what an electronic design is, but that's where it's at. So with that, as I said, we're taking this forward. We're taking it from memory products. We are getting customers now in power, silicon carbide GaN customers. The next step is advanced CMOS. As a matter of fact, we're starting to develop this for advanced CMOS technology for customers of us that you'll see the application of this is going to be huge for manufacturing, especially semiconductor manufacturing, and that's where we are taking this. So to summarize, we do enable the next generation of products. We actually work in the advanced R&D teams of the companies that we work with. 95% of our revenue comes from. We do utilize AI. We have successfully implemented it in generating these accurate digital twin models. And we actually, as I said, the space we work in, we do from atoms to systems. Our systems physically being only a wafer at high level or a panel for a display in this case right now. And we have worked on these problems for the past 3 decades. The other thing that we do that differentiates us and our customers come to us is we do what's called agile R&D. So if you have a specific I gave you an example of silicon carbide again. There are 40 flavors of each of these, right? If you have a flavor that you cannot really simulate or implement to get it to production, you can come to us. We help you predict whether that can be done. We do add a customized module to our platform to help you get there, and that's how we do part of our projects and businesses. So with that, I wanted to thank you for your time. I hope I did not go too fast. And again, for Saturday afternoon, I hope this was enough. So thank you.